1593. March 14. The cliffside overlooking the Han River is freezing. The air above the Ha-Engju fortress is thin and carries the metallic taste of ozone and impending combustion. Below the wooden stockade, the soil vibrates, not with the natural tremors of the earth, but with the rhythmic, synchronized impact of 30,000 armored feet. The Japanese 1st Contingent, led by Konishi Yukinaga, advances up the narrow incline. They are veterans of a century of civil war, a unified killing mechanism equipped with Portuguese pattern, ARQ buses and hardened steel. Inside the fortress, the logistical reality is grim. 2,300 defenders stand against 30,000. The ratio is 13-1. Survival is a mathematical impossibility based on conventional infantry tactics. But the defense is not relying on conventional infantry. Arranged along the ramparts are 40 rectangular wooden carts. They smell of pine resin and tar oil. These are not static fortifications but mobile artillery platforms. The crews stand ready, their hands stained black with carbon and sulfur. They do not look at the faces of the enemy surging up the hill. They look at the fuses. A single command cuts through the cold air. The operator steps back, covers his ears, and pulls the ignition rope. The result is not the singular crack of a musket, but a tectonic roar. In seconds, a single cart disgorges 200 rocket-propelled arrows. The sky darkens as thousands of projectiles arc over the ramparts, a manufactured storm of iron and fire plunging into the dense formations below. The physics of the battlefield shifts instantly from linear infantry, maneuvering to area saturation. The Japanese advance does not halt, it evaporates. The mechanism responsible for this devastation is the Hwacha. It is a triumph of primitive engineering, a synthesis of chemistry, aerodynamics, and structural carpentry designed to solve a specific tactical problem, the defense of a peninsula against numerically superior invasion forces. To understand the violence of the IMJ in war, one must understand the machine that defined its most desperate hours. The Hwacha was not a crude firework display. It was a precision instrument, the result of a century of rigorous scientific development, initiated by the Goryeo military officer Cho Mu-song. In the late 14th century, the geopolitical reality of Korea was defined by the monopoly on gunpowder held by the Ming dynasty. The Chinese regarded the formula as a state secret, restricting trade in nitrous raw materials to maintain regional hegemony. Cho engaged in industrial espionage, bribing a Chinese merchant named Li Yuan to obtain the purification methods for potassium nitrate. This act of intellectual theft was the genesis of the Hwacha. It allowed for the establishment of the Hwadong Dogam, the government office for gunpowder and firearms, in 1377. Here, the chemistry of survival was perfected. The propellant used in the HWAC has projectiles, the Singai Joan, relies on the rapid oxidation of charcoal by saltpeter. The chemical equation governing this reaction is brutal in its simplicity. 10 molecules of potassium nitrate react with 8 of carbon and 3 of sulfur. The result is potassium carbonate, potassium sulfate, and a rapid expansion of nitrogen and carbon dioxide gases. This exothermic process generates the thrust necessary to overcome gravity and drag. The efficiency of this reaction depends entirely on the purity of the ingredients. Joseon chemists extracted potassium nitrate from nitrogenous soil found in caves and beneath floorboards where organic decomposition was high. The extraction process involved leaching the soil with water and wood ash, precipitating calcium carbonate and leaving a solution of potassium nitrate. This liquid was boiled and cooled, allowing the crystals to form. The purity required for consistent rocket flight meant repeated recrystallization. Impurities such as hygrospocyl calcium nitrate would absorb moisture from the air, ruining the powder. The charcoal acting as the fuel was derived from pine or willow, chosen for its cellular structure which provided a vast surface area for the flame front to propagate. Sulfur acted as the thermal catalyst, lowering the ignition temperature and increasing the combustion speed. The physical form of the propellant was as critical as its chemical composition. Early gunpowder, known as serpentine, was a dry mixture of fine dust. This presented a logistical nightmare. During transport in wagons over rough Korean terrain, the vibrations caused the ingredients to separate based on density. The sulfur settled to the bottom, the charcoal rose to the top. A keg of separated powder would not explode, it would fizzle. The solution was corning. Hoseian engineers mixed the powder with liquid, often water or wine, to form a paste. This paste was pushed through a sieve to create uniform grains, then dried. The resulting granules were physically durable and chemically stable. More importantly, the spaces between the grains allowed the flame to travel instantaneously through the charge, ensuring that the entire mass deflagrated simultaneously. This consistency was the difference between a rocket that flew 100 meters and one that flew 450. The projectile itself, the Sing-Ai-Joan, was a marvel of aerodynamic stabilization. It was not merely an arrow with a firecracker attached. It was a nozzle-less solid rocket motor. The main body consisted of a bamboo or wooden shaft, varying in length from the small 1.1 meter variants to the massive 5.3 meter large variants. Attached to the shaft was a paper tube filled with the black powder propellant. The paper was not ordinary writing material, it was a structural component, layered untreated with resin to withstand internal chamber pressures that could reach several megapascals. Without a modern de-Laval nozzle to constrict and accelerate the exhaust gases to supersonic speeds, the Hoseian engineers relied on the mass flow rate of the combustion gases. The internal geometry of the powder grain, the surface area burning, at any given microseldon dictated the thrust profile. A long, narrow combustion chamber increased the propellant stay time, ensuring complete combustion before the gases exited the rear of the tube. Stability in flight was achieved through fletching. Large leather or parchment feathers at the tail of the arrow moved the center of pressure behind the center of gravity. This created a restoring force. If the rocket pitched up, the air resistance on the tail pushed it back down. Historical records indicate that the Sing-Ai-Joan experienced the Magnus effect, where the spin of the projectile created a pressure differential, causing it to deviate. Watch operators were trained to account for this, adjusting the elevation and azimuth of the launcher to compensate for aerodynamic drift and wind conditions. The accuracy was not pinpoint, but it did not need to be. The Hwacha was an area-denial weapon. The Lonpax, a wooden block drilled with up to 200 cylindrical holes, functioned as a collimator, aligning the initial trajectory of the volley. The fuses were linked in a complex master train. When lit, the flame raced across the back of the array, igniting row after row in a cascading ripple of fire. The tactical deployment of the Hwach at the Battle of Ha-Ing-ju demonstrates the friction between superior engine, daring and overwhelming numbers. The Japanese forces under Kaito Kiyomasa did Teihai-dai were battle-hardened, their tactics refined during the Sengoku period. They relied on the coordinated use of the ARQ bus and the spear. The ARQ bus was a terrifying weapon, capable of piercing armor at close range, but it suffered from a slow rate of fire. The Japanese doctrine relied on rotating ranks of musketeers to maintain a continuous barrage. Against this, the Koreans pitted the Hwacha. The terrain at Ha-Ing-ju forced the Japanese to attack up steep, narrow slopes. This channeled the enemy into dense columns, negating their numerical advantage and creating the ideal target profile for saturation fire. A single Hwach, a volley delivered 100 to 200 arrows into a concentrated kill zone. The terminal ballistics of the Sing-Ai-Joan varied by type. The small Sing-Ai-Joan, used in the hundreds, was a kinetic energy penetrator. At a range of 450 meters, the arrow retained enough velocity to pierce traditional armor. The medium and large variants carried an additional payload and explosive warhead. A secondary fuse, timed to burn slower than the propellant, ignited a charge of black powder upon impact, or at the end of the flight trajectory. The medium Sing Ijeon's warhead was powerful enough to create a 30-centimeter crater in sand. Against biological targets, the effect was catastrophic. The explosion did not just generate shrapnel, it created a localized overpressure wave and a thermal flash. The psychological impact of this weaponry cannot be quantified in joules or meters per second. To the Japanese samurai, accustomed to the crack of muskets and the clash of steel, the hwacho was a horror. It produced a deafening noise, a screeching roar that signaled incoming death. The smoke from the discharge obscured the ramparts, turning the Korean defenders into invisible agents of destruction. The hwacho itself was a triumph of logistical engineering. Built from pine or oak, the cart was rugged and modular. The wheels were fastened with iron axles and wood pivots, lubricated with tar oil to reduce friction during transport. This mobility was crucial. Unlike the heavy European bombers or the stationary Chinese rocket batteries, the hwacho could be maneuvered by 2 men. It could be redeployed to threaten sectors of the wall, pushed up steep inclines, and retreated when lines collapsed. The Lunpax was adjustable, allowing the operators to alter the angle of fire from a direct, flat trajectory to a high-arcing parabolic flight path. This versatility allowed the hwacho to strike enemies hiding behind cover or to sweep the open field. The Korean Army included siege engineers and blacksmiths specifically tasked with repairing these machines in the field, ensuring that a broken axle did not mean the loss of a strategic asset. However, the hwacho was not without its limitations. It was a fair-weather weapon. The hygroscopic nature of the black powder meant that high humidity or rain could render the weapon useless. Moisture absorbed by the paper tubes caused the powder to cake and burn unevenly, leading to squibs or catastrophic casing failures. The effective range of the small Sing Ijeon dropped from 450 meters to less than 100 meters in poor weather conditions. During the IMJN War, there were instances where the weather dictated the engagement. If the rain fell, the hwacho fell silent, and the Koreans were forced to rely on their bows in the terrain. Furthermore, the reload time was significant. Loading 200 arrows, ensuring the fuses were linked, and priming the ignitors took time that was not always available when an enemy was scaling the walls. The defense of Haeju succeeded not just because of the weapon, but because the terrain forced the Japanese to attack in waves, granting the Korean crews precious minutes to reload between assaults. The naval application of the hwacho reveals the adaptability of Joseon military doctrine. Admiral Yi Sun-sin, the architect of Korea's naval dominance, integrated the weapon into the pan-okase on warships. The flat, stable decks of the pan-okase provided a suitable platform for the recallist's launch of rockets. In the chaotic environment of naval combat, where ships pitched and rolled in the swell, the saturation fire of the hwacho was more effective than single-shot cannons against the personnel on enemy decks. Operators stationed on the main deck or firing from the rowers' windows could target the sails and rigging of Japanese ships. Incendiary Sing Ijeon could set fire to the wooden canvas of the enemy fleet, causing chaos and disrupting their formations. At the Battle of Noryang, the final engagement of the war, the combined firepower of cannons and rockets annihilated the retreating Japanese fleet. The Sea Burn. The legacy of the hwacho is preserved in the Gukeijo or Yiseorai, a text from 1474. It contains schematics of such precision that they utilize units as small as 0.3 millimeters. This is not the documentation of a primitive folk weapon. It is a technical manual for an advanced aerospace system. It details the thickness of the paper, the grain of the wood, the composition of the glue. It is a testament to a society that valued scientific rigor as a means of national survival. The recovery of these plans in the modern era allowed for the experimental reconstruction of the weapon, validating the historical accounts. The reconstructed Sing Ijeon flew true, their ranges matching the records, their warheads detonating with the predicted force. The myth was stripped away, leaving only the cold, hard engineering. The IMJ in war decimated the Korean peninsula. The loss of life was catastrophic. Arable land was reduced by 66%. Famine and disease followed the armies. The cultural loss was immeasurable. Palaces were burned, archives destroyed, and skilled artisans captured and taken to Japan. Yet, the Joseon state survived. The invasion that was intended to sweep through Korea and conquer China was halted. It was halted by the strategic brilliance of Admiral Yi, the resilience of the righteous armies, and the intervention of the Ming. But on the ramparts of Haeungju and in the mountain passes of the north, it was halted by the Hwacha. The evolution of the Hwacha ended with the war. The peace that followed saw a stagnation in military development. The urgency that drove Cho-mus on to bribe merchants and King Sejong to standardize rocket production faded. By the 19th century, the technology had been eclipsed by Western rifled artillery and smokeless powder. The wooden carts rotted, and the paper rockets disintegrated. But for a brief window in the 16th century, the Korean peninsula was defended by the most advanced multiple-launch rocket system on the planet. A weapon born of necessity, fueled by chemistry, and delivered with the cold, mathematical precision of total war. The Hwacha remains a silent sentinel in the history of ballistics, a wooden precursor to the steel rain of the modern battlefield. The smoke clears, the noise fades, but the physics of the trajectory remains absolute.